Halo,
Halo.
welcome live.
AU.
Yuk, sudah online sekarang.
Ya. Moderatornya malam ini Mas Abai.
Menunjuk aja sebenarnya.
Well, thank you so much for the times. And today we have already in broadcasting on air. Which our presenter today is Emmanuel Sanka, master student at Uppsala University. For today, we will have presentation about Carapace surface architecture facilitates camouflage of the decorator crab Tiarinia cornigera. This journal has already been published in Acta Biomaterialia at 2016, which has been supervised by Eko Agustiono, Adalfario Formular, and Barves Alams. So, okay, the time is here, Emmanuel Sanka, to explain about this journal. Thank you so much.
Okay, so maybe I can start. Now, yeah, from the beginning, my name is Mano Sanka. Thank you, Pram, for the introduction. And actually, we did this research in 2015. And when I came to Finland as a visiting researcher, I got the project about this decorator crab. But what kind of research that I did? Okay, thanks, Ron. I did already. So yeah, first of all, maybe can you mute everyone, because I can hear my voice.
Okay, well, for everybody that
or it's from YouTube, that I still hear my voice presenting. Okay, so I can start now. Okay, thanks. I did already. So yeah, first of all, okay, I can continue, or you're still managing with this
yeah, you can continue.
voice. Okay, because I can still everyone, because I can hear my voice.
Hello, is there someone that's still using YouTube? Or this voice coming from yours, I mean, Sanka? I don't know.
Mine.
Have you opened YouTube? No?
Okay, yeah, maybe mine. Okay, so yeah, we can continue. First of all, yeah, about this thingy. This is a crab, and we can see the algae there, and it's a bit weird, right? This is like the other crab, but has some feature, but we have to find what it is first. So what is it? Maybe you already read my paper. Yes, this is a decorator crab, which can decorate itself by adding some algae and some stuff there, so it can have the camouflage. But how the mechanism behind it? So I will just talk like around 5-10 minutes, so it's not that long, but let's see how it goes. Yeah, that biofilm is actually from the bacteria or a microorganism which has the some compound which can then have the addition interaction with the surface, which in this picture we can see the like the bacteria then settle and find the biofilms, make the biofilms, and then the other thing that can attached to the biofilm, and we can see easily on the surface of the boat or something similar, which we can see in the surfaces. Then also here, this is one of the example that the algae then can attach. So basically, this is not just a macroalgae, but there are some microorganisms, which also bacteria and microalgae, which can attach first, and then after that, the bigger stuff can attach. So yeah, here we can see it. Also, like we can see the barnacle in the surfaces. So that's why it's not just the barnacle that attach from the spore, but also there will be an initial interaction before that. That's why in this occasion we tried to find out what kind of interaction or what kind of relation between the surface and the algae, which can stimulate the biofueling that may lead to the camouflage that decorator crab has. So, yep. Before doing that, we had to know what kind of species of this decorator crab, and then we also wanted to find the physical surfaces or interaction which may lead to the biofouling, and also the chemical study because it's related. So let's find it out. From species identification, why we should do the molecular identification, because this decorator crab is hard to determine by its morphological structure. So if we if we see here, there is a key part identification which in this part which called rostrum, but we have to brush, and it may also lead to the different kind of thing, because when algae attach, maybe like some barnacle attach, so it's hard to define what kind of species of this creature. So yeah, we did the species identification with the DNA barcoding, and we defined three different primer. We used three different primer, which one 16 acids from mitochondria and 28 as from nucleus, and one barcoding primer, which is universal from cytochrome oxidase 1. And from this result, we got the first one, which directly relate with the Tiarinia cornigera and has a smallest distance, and we compare with the other from the 16S, which is from the mitochondria. Also, these lead to the two different species of Tiarinia, and then we confirm it with the nuclear database from 28S, and it also lead to the Tiarinia, which has the species which is cornigera. So from this result, we are sure that the species that we research was from Tiarinia cornigera. And this barcoding method, it's actually not that hard, because you just use the universal primer, which available from previous research, and then you run it in a PCR, and you'll get the sequence, and then compare it with the gene bank or available database. Then the physical analysis, the most easiest, not easiest, I mean, maybe is just more what I can call it. So we can use it and define the surface easily with the scanning electron microscope. Here we got 4 different magnification, which also lead us into different kind of structure or level of structure in the carapace surface. And we can see here this is like without any treatment, and loads of stuff stuck there. And we can see also maybe here with some microalgae diatom and loads of stuff. But then we got another treatment with the ethanol, so it might get rid of like some stuff like which has chemical interaction, so we can only see the physical structure of this carapace. So yeah, from this structure we can see that the biofouling may supported by this interaction with the physical interaction on the carapace surfaces, which can have haystack and stuck other things there, and then more, and then you'll get another layer there. But let's see how it goes further. A bit further. Then from this physical structure, we tried to model it. So I picked one of them, like I thought it would be the C one, and then took just only a tiny part, and then I draw in a ImageG software to have these 2D structure from the above of the carapace, and I did the computational fluid dynamics simulation, which give us the clue about how the fluid goes from many sources. So we can see here, we can have the vertical and horizontal fluid flow. And as we can see that the flow will go upon the space between the haystack structure, and on the red box we can see the nucleation, which give something well, in easy way it will give the stuff, or like something when it flows with the water, it can stuck there and then lead to the biofouling process. So yeah, from the physical analysis we got these things. And we tried to define another thing, and from the chemical perspective, we did the from the SEM, we also did the EDS, or to find what kind of compounds from the or elements on the carapace surfaces. And here we clearly from the A, there are 2 different elements, which one is from the mineral with the red one, and the second one from the organic material, which may be from the proteins or some other thing that secreted by the crab to form the carapaces. And there are some pattern, but we couldn't define how they have these haystack structure. But then from different magnification, it's a bit further, then we can see that this is like a flower that stick up from the inside of the carapace. So yeah, actually the crab also produced the organic material, like a hair, which will be covered, and we can see here on the figure C, will accumulate the other things and then form like a haystack that we saw before. So yeah, We can also see some diatoms there which stuck on the surface. Then we tried to define and to study more about these feature by its chemical, and then we did the FTIR, or Fourier transform infrared, to find what kind of compound there and from the carapace. So we crossed it and then we put it in FTIR and we got this graph, which lead to like very interesting, because we got the NH group here, which may lead to the proteins which have like which may interact with the other stuff there. We can also see that these peak will define the carbonate and other stuff like silica, and yeah. And then we also confirmed that one of the peak is beta chitin, which we know that in every carapace of crustacea they have the chitin, which may defined by beta and alpha chitin, but most here we just spotted on beta chitin. From this study, we modeled and tried if the compound from microorganism like from bacteria and microalgae, which interact with the chitin from the crab, sorry. And from this one, we picked from four different chemical, which mostly found in the microalgae, which mostly was carbohydrate. Yeah, glucan chrysolaminarin, glucuronic acid, galacturonic acid, and manuronic acid. From these from these carbohydrates, we put it in a beta chitin pleated seed. So the molecules can interact with the beta chitin by using mechanical dynamic simulation with quantum optimized interaction. And from this picture, we can see even one of them just sticking out like that, but all of them have the van der Waals interaction, which can be found from the gecko, or which can climb the wall with its van der Waals interaction. So once it sticks to the beta chitin, it will be stuck there and hard to release from the beta chitin. So yeah, we compared four of them, or even the electrostatic interaction. It's not strong enough to hold the two molecules, but they have significant van der Waals interaction. So that's why we stimulate like this interaction may also give more ability for the microalgae to stick on the carapace, and then it will have more biofilms there, and then attract another biofouling subject to stick on the carapace, and then we can see on the crab that they have this feature that algae can attach on it. So yeah, for the conclusion that not only in the structure from the decorator crab that can attract the biofouling process there, but also the chemical interaction and how the environment put physical the physical interaction, which in this case we got the fluid dynamics that can flow around the carapace and stimulate the biofouling process. So yep, that's all. So we conclude that the camouflage mechanism is not only from the structure but also from the chemical interaction and from the environment physical interaction. Yep, that's all. Maybe.
Okay, well, a little bit interesting about the chemical interactions, fluid dynamics, and because some organisms that living together with other organisms, they must be interacted each others, and from that interactions we should know, or uh, we should take some informations about what kind of interaction that has been happened within each other. Is this synergism interactions, antagonism interactions, or maybe some another interactions? For in this case, maybe the interactions between the crabs and then the dynamic environments, and then with the microalgae, microbia, they make some such as kind of interaction to help the crabs to camouflage in their environments. Very interesting. And also for some, talking about the microorganisms, some microorganisms also produce such as compound that if it can be an anti-fouling or something else. Well, okay. For some people or for some viewers or listeners that would like to asking about this kind of research topic, onegaishimasu.
Yeah, feel free to ask anything.
Is there any question?
Yep. I have some question.
Okay.
Yeah, first, congratulations for your paper. It's super cool project. You're really
Thank
cool.
you.
Yeah, I just want
Thank
to
you
ask.
very much.
Yeah, well, this is very interesting camouflage. I mean, you know, I just want to ask: is it possible this crab is actively attached anything material like among its habitat? So like they attach by itself. It's not passively attached, but actively attached. So they like hook something in environment and attach to its carapace. Is it possible? Or it's
Well,
just like passively they just okay, you just I'll stay here and that's algae will attach in my carapace or something like that.
okay. Thank you very much. Yeah, we actually we witnessed the how these crab were just stuck something on its carapace, but then we couldn't like put it here because first we have to study more about the behavior of this crab, because they also eat the algae. So that's why is it just like stucking and then make them have more algae, or just want to have the camouflage and avoid the predator. But yeah, that's interesting study to have in a future, because when they have these passive mechanism for the camouflage, it will give them more benefit for the energy, like not just to find more algae to attach it on the carapace, but also they can easily have the foods on their carapace, and it's just interesting. But yeah, we witnessed how they put stuff on their carapace, but it's not stuck. It wasn't stuck in the carapace, but
Mhm.
at least they tried to two things there.
Yeah,
But yeah, after this study, we're sure that maybe not just the active, but also the passive interaction may lead
yeah,
to the
yeah, maybe.
biofolding and camouflage mechanism
Yeah.
of this crab.
It's because it's very unique. I mean, in terms of their adaptive mechanism in environment, they can
Yeah.
they can like camouflage. They cover it up. There's their carapace with algae and hide,
Mhm.
and
Yeah.
and they have like structural things that unique. Also, chemical
Mhm.
stuff. It's very unique.
Yeah.
And I
Yeah.
just know that this species is the decorator crab. Like it's been a while.
Yeah, yeah. And also, okay, it should be noted that not just the algae there. We can see it like maybe sponges, and if the structure is was it suits enough for the uh, for the for the like things like when we can say corals that can attach to that
Yeah,
surface. So yeah, it's also can be like that.
yeah, coral, maybe. All right, thanks.
Yeah.
Okay, well, thank you so much, Mr. Abay. Any others would like to have having any questions? Early?
Uh, yeah, I have a question. Not
Okay.
a
Please
question,
don't make
several
any
questions.
signs. Just
By the
asking
way,
about it.
yeah, thank you for sharing, Sanka. It's really interesting topic, and it's like quite new for me because I never studied about biofouling before. So, my question is most about like focus about this decorator crab structure, the surface structure, because it's quite interesting. And do you think the structure is come from their conduct that's kind of structured by themselves, or the structures come from the accumulation of the, let's say, chemical stuff in their environment? So that's my first question. And my second
Okay.
question is, um I really I really like the picture, some picture. I mean, like it's so beautiful, and for that structure, have you analyzed the, let's say, crystallography or the structure of that, and or do you know something about the yeah, like I said, about the structure, the information of the structure? Because because I think you got that kind of pictures. You will get that kind of picture from the anorganic compound. It's usually from anorganic compound, as far as I know. If that anorganic compound, how can algae attach through that compound? So, I mean, yeah, maybe you have what you have poison or something.
Okay.
Yeah, so that's my question.
So thank you
Thank you.
very much, Irv. Yeah, based on this picture, yeah, I can start from this picture. Well, from this picture, actually, the crab has and gave us some clue about the hairy structure from the carapace. So you can see here, if you see my pointers here, there's a hair sticking out from the carapace,
Where is your
and then
pointer?
here,
The black
this is
one.
my pointer,
Okay.
and then I put it in the figure T here. Sorry, and wait, here there is a hairy structure
Ah, I see, I see. Here it is.
like, and there is something like just want to cover this thing and then make it like this, the other one here. So yeah, and this was confirmed by the EDS scanning diffraction. I'm sorry, EDS is like energy dispersive X-ray spectroscopy, I think.
Yeah.
Yeah. and it scans how the mineral leads from this area. And if I'm isn't wrong, yeah, here we can see it like from this hole. We what is it? We're not sure, but we guess that the hair that we saw before was sticking up from this part, and then there will be like some secret from the organic material there, which depicted on the green color, will cover and then make this kind of hairy stuff and cover the hair. So I think that's the first mechanism before the other things will attach to this structure and lead to other biofouling process. So yeah, is that answering
So
your question?
how
And this is the mineral.
what's the function of the hairy then? Because it's like, what's the function of the hairy then?
The hair, like the hair from the carapace.
Yeah.
The hair form of the carapace.
Yeah, we're not sure actually, because when we clean it, the structure, there will be like two of them like this. The first one is just hair, and then one is covered. So maybe it's just to have the haystack structure, and may lead the coverage of the organic material from the inside of the carapace will lead just only from that hair. So we can see it here, it's separated between one and the other. But if there's no hair here, it's just sticking out and then spread out around the carapace, and there will be nothing happen there. So yeah, maybe that's
Okay.
thing as far I can
My first
say about it.
question
The second question.
is that no, it's my no.
Which question, Lee? Hello? Hello, Lee?
Yeah, can you hear me?
Yeah, I can hear you. Which question?
For the surface structure of this crab, does it conduct by itself, or it's like because of the accumulation of the chemical compound in their environment?
I see. Sanka, that's the question
So that's
from
my
Ali. About is there any kind of interaction? I mean, another organic compound or something else. So the structure have shape like that's one. Hello, Sanka. Hello, Sanka. Sanka, I think you mute your.
Okay.
Yeah, can you unmute?
Okay.
Okay.
You can hear me now?
Yeah, I can hear you. Okay,
Yes.
about the question from earlier. Is there any kind of interaction from organic compounds so make the structures in the surface of the carapace having a structure like that's one?
Okay. Yeah. From based on the scanning electron microscope and the ADS, these structure can be accumulated from the two sides. First from the environment, the second is from the carapace itself. Because here we can see there's the organic material that sticking out also. The one that I said that this hole may lead to the hair that's sticking out from the carapace, and then this thing is from the crab itself. But there will be a possibility also, like the other things from the environment also support this haystack structure. Well, we can say production, but like formed, that can be formed from the these hair, and then from the organic material from the carapace, and also from the other microorganism or elements that just sticking to the that just stick to the hair or haystack structure, or we can say this feature. But yeah, there is a possibility for that, because as we can see from the model also, we just modeled 4 of them, and then they are all stick. That's the thing. So yeah, because once it's stick, it's hard to release from, like, maybe the other compound will also stimulate other interaction with these chitin, which mostly found in the carapace. So yeah, is that answering your question? That was answering your question, or?
Yeah. Thank you very much for your explanation.
Okay. Is there any questions?
Hello.
Okay, no, you can
Yeah.
ask.
Sorry for if I didn't really paying attention. Just want to ask: does the crab itself secrete certain chemical compound to attract the algae, or is it just the crab shell structure that favorable to the algae?
Very
Okay.
nice questions.
Yeah, nice. Well, actually, the first thing that we are sure, from the environment, will stick to the carapace from the crab, but we couldn't we couldn't find any study that determine about this organic material which we found on the carapace, which may also lead to the algae biofouling in or algae falling in this carapace surfaces. So it may, well, we can say that it may involve everything in the environment. So not just actively secreted, but also passively added from the environment, because maybe they interact, and from this model they interact, and all of the molecules from the algae that was represented as a sticking agent, they can stick on the carapace, or beta-chitin, which represent as a carapace surface. So yeah, is that answering your question?
How about the answer? Ibnu, have you already got the point? Hello, Ibnu. Can you hear us?
Hello. Hello.
Hello. How about the question? How about the answer? Is already answer your questions?
Yeah. Thank you. So there
Okay,
is still a lot to discover about this compound.
Yeah, there's a possibility.
Yeah, so many
Because-
possibility.
Yeah, because we can, well, we know, like, compound, not just compounds, maybe from the environment we can see loads of stuff, or we can have loads of stuff happening, interacting, and then if they secrete stuff, maybe also have more interaction on this specific surface or part of the carapace. Is there any other question?
Yeah. Hello.
Mm-hmm.
Yeah, I just want to add some like experience, because like in coral, before they attach to, let's say, like a reef foundation, there are a lot of algae, and they produce a lot of chemical cues. I don't know, like specific cues. What's that? It can be
Sorry.
chemical compounds, but it's like attract coral to attach to the algae. So maybe it can be happen. I mean, it's possible. Is there? I mean, there's any chemical cues that make this algae attached to this crab carapace? Possibly.
Yeah.
I don't know,
Yeah,
but
yeah, yeah.
it can be happen in nature.
Yeah, we can see from this picture too, like there are like the biofilm is just the initial layer from the microorganism, which may also bacteria, but also microalgae in this case. But yeah, and the biofilm molecules that we modeled is were from the microalgae, which mostly from the diatoms, from its attachment. So yeah, the first initial, which also lead another attachment from maybe bigger like organism like protist, or here we can see barnacle maybe also attached, and then other things followed.
I think
Mhm.
there is interesting point in this picture that we can take. Have you ever trying to look for some journal or something else, especially about the typical bacteria that producing the biofilms in the surface of the carapace of this crab? Do you know what kind of bacteria that always attach to the surface of the carapace?
Kind of bacteria.
I mean,
Actually,
what kind
I'm
of
not sure.
hmm?
I'm not sure about the bacteria, but we studied based on the diatom, because first they're heavy, like compared to other microorganism, because it has the silica cell wall, so it may just go down to the bottom. But then after they go, like maybe, well, we can say that this diatom just fall to the carapace, it also produce the compounds that may lead to the biofilms. What is it? Production. Biofilm layer production. Yeah. So yeah, we model it based on the research from the diatoms that have the sticking agent.
I see, I see. Yeah, just some information for some people that very interested with kind of bacteria that producing biofilm or something else. It should be very interesting because yeah, you can isolate the bacteria that living in the surface of the carapace and then trying to know what kind of the bacteria and then trying to make some applied bacteria maybe to produce some biofilm that yeah, very interested. Okay, another questions maybe from Adit or yeah, I'm sorry. Exactly, Mbak Fauzia. Just they would like to you just only review side by side from your presentations. Well, what is it?
What is it?
Started from the first presentations and then second presentation. Yeah, just side by side. And because Mbak Uzi just connected.
Missed the presentation. Okay.
Yep.
Yeah, this is just to see what it is and how this weird deed thingy appear. What is that? And
then for the next
yeah,
one, this
we
is
know that this is a decorator crab,
it has
but
been
how
known as
they
decorator.
decorate themselves.
I see. And then the next
And
slide is
then yeah, the introduction about the biofilm that may lead to the biofouling. And then we can see here the example how the biofouling, because it's not just annoying, but it will give, yeah, it will give more weight. And then if you have like these things in your boat, it will take more energy to, and then take more fuel, and you have to give like or spend more money to have your boat
clean
going. Yeah, so or cleaning.
Mm.
But I think they won't clean the boat from this. But yeah, from the structure we know that it could be something there, not just the algae, but maybe the surface that also have on the that also from the carapace or from the crab. And we did the species identification, physical analysis, chemical study, and yeah, we did this identification through the barcoding method. and the physical analysis with the scanning electron microscope, and also fluid dynamics modeling. Well, in a simple way, I just model how the water flow from one plant, like no, or from one is it? From one side to other side, yeah. Like here, vertically, horizontally. We did also like diagonally, but we didn't need it for this paper. But yeah, from this point, we can see like there is a nucleation there, like maybe part that can accumulate the stuff. So in this case, maybe the biofouling agent. And also we did the chemical study. So in this picture, we can see the organic material and the mineral that have, well, we can say that almost most of these Carapace surface without the dots here are the mineral from carbonates. But then when we see here, this is this green part is the organic material structure. Yeah. And this is just another SEM structure. And we can see here when the first SEM picture that early asked about the hair stuff that may sticking out from the carapace will be covered with the organic material. And we found that the algae stick and then stuck, not just stick, but stuck on the surface of this carapace. So this is a diatom there. Like maybe other things, but we just spotted the diatoms. That's why we modeled with this interaction through the mechanical dynamic simulation and from the beta. And we also found that these FTIR, actually this Fourier transform infrared spectroscopy is to find the absorbent based on the compound that we put on the spectrophotometry. And we found that these beta-kinin interaction on this peak. So that's why the most of if you've tried to search the journals or articles, like most of the carapace, crab carapace consists of the beta and alpha chitins. So we picked this beta-chitin and then model it with the molecules from the diatoms that have the sticking agent. Not sticking agent, but yeah, they can stick to stuff like this. So yeah, we found that they stick on the beta-chitin plated sheet. So this one is beta-chitin, and we can see it here. Even though the electrostatic interaction is not that strong to stick them all, but there were the van der Waals interaction that may lead to the biofolding. That's why we modeled the fluid dynamics. Once they stuck on the nucleation here, and they have the capability of or stimulate the van der Waals interaction, they can just stop there and then get more and more and then have another layer. So yeah, I think that's all.
Okay.
That's why we concluded not just structurally but chemically and the environment phenomenon that can lead this camouflage mechanism.
Okay. Bauzi, do you have
Mhm.
any question?
Yep. I was late, so I'm not sure if you already mentioned about it or not. I'm wondering how big is the possibility of variance in the structure, I mean the attachment structure, because it's I mean by algae and also crab species, there's so many algae species in
Mhm.
this direction, right? So how big is the possibility of the structure? Is it always different between algae species or for the species, and also the environment factor like pollutants maybe? Is it
Yes.
affects this structure?
Well, I'm not sure about that, but if we back to the concept of the biofilm, here how they how they form and then get the interaction between one and another, it may be affected by lots of stuff, including the environment. So maybe the pollutants, if the bacteria or microalgae wouldn't or cannot grow in that environment, so there will be no initial biofilm. There will be no forming of the biofilm, so bigger things wouldn't attach on the surface because it needs to be the in like here we can say it needs to be like layered that may give more interaction. We modeled only one molecules there and it leads that attachment, so maybe if like more of them, like, and then bigger pleated sheet, it will also give like more interaction, so that's why it can hold the other things there. But if the environment not support these things, it was just no interaction there. So I think that may answer your question.
Yeah, because maybe this structure is useful for the crab identification, right? So
Yes, for sure. Yes, that's
so
why. Uh-huh.
if the structure keep changing, uh, because different algae, different environments,
Yes.
so it might not really good for identification.
Yeah,
Is
that's why we did the species identification with the DNA barcoding, because uh, after we got the family and the
Mhm.
genus, we tried to compare, and then there was like different or huge different after we clean everything from this carapace. So yeah, we confirmed it through the barcoding, and then three of them is lead to the species, genus and species. So we are sure that these also affect the biofolding process or carapace forming.
And I want to know like how many samples you work on for this structure, and also how many place to take the samples.
We only did one because it could be different from one and another.
Yeah.
So we just confirmed like from one species, and the barcoding was like used one. No, we just took like one sample from its legs, because one of the methods that we cited was suggested that we got it from that part. And yeah, we used the carapace to define the structure. Only
So
one.
so the samples come from the same pitch.
Yeah.
Okay.
Mm-hmm. Because it could be different actually,
Mm. Yeah.
but yeah, But from this sample, we can see it. It may represent the decorator crabs, but from the interaction, we can see that there will be loads of other possibility. But from this sample, that's why we tried and defined the species, because it could be different.
Yeah.
We put also where we took the samples from
Thank you.
in the article.
Okay, well, is there still any question? Nothing? Adit? Okay. Well, I think that's very nice presentation, Sanka, and thank you so much. And also, I would like to say good luck and the best for the paper that has been published as you as the first author. And I hope this paper also can motivate us that science without, I would like to say science without publications is like, what is it? It's not no, just science should be published, because every time knowledge has changed by the time. So yeah, it should be published, and we should write about everything that we have done to learn about the science. And for all the people's
yeah, just want to add something.
From
this study, actually, my background is just from the species determination, but my supervisors suggested a lot. So that's why I studied this chemical interaction, fluid dynamics, even the physical structure of it. So there will be loads of possibility for research. That's why don't put the boundaries, even like the things that you wouldn't expect before. So just think without boundaries, and then you'll find what will come ahead. So yeah, because I never did those kind of things before.
As I forgot some statement from Prof. Taifu Mahmud. Maybe I did know about him. This is one of Indonesian researcher that now has worked in Oregon State University, United States. He ever said, "Science without borders."
Yeah.
So science should, because science is very, very wide, and we cannot make some square to make limitation of science. Because one science branch, they have correlations with the others. So physics, chemical, biology, mathematics cannot be separated each other. They are included in one. The name is science. Well, thank you so much for the night that has been given to attend in these presentations. Thank you so much for Emmanuel Sanka for the presentation. That's very wonderful. And also I would like to say for Bauzi from Tsukuba University, early from UK, and then Adit from Indonesia, and then Mas Ibnu from Indonesia, and also Mas Abai from Australia. And God willing, we can meet again next 2 weeks. If there's any change. Next 2 weeks, right?
Yep.
Yeah, I hope we can.
After my exam.
Yeah, please tell us if there's kind of exam that should be free. So yeah, we can manage for the biological journal clubs. And also, yeah, thank you so much for this night, and see you later next 2 weeks. Bye.
Bye.
See you. Bye. Thank you.
Thank you.
Turn off the live.
Thank you.
Thank you. Mas Abai, please.
I'll turn off. Yes. Now.
I mean, off air, please.